So in this section, we talk about the idea of linear correlation. What does it mean to say that two variables have a correlation? Well, when we say if there's a correlation, what that means, what we're actually looking for is a way to quantify how closely can we say that one variable correlates with another. In other words, as one changes and the other changes, can we say that one actually affects the other? Well, statistically, we can come up with a number that kind of explains that, and we call that the linear correlation coefficient. You recall that in the last section we talked about the idea of r squared. Well, the square root of that is called our linear correlation coefficient. And for a set of n data points right here, if we actually went through and found the linear correlation, there's this big formula. Oh, look at that. That's really there for the shock value, isn't it? That R correlation value is what we were actually finding in our last sheet. Now, I'll show you there's a quick and easy way to get this in Excel, and we don't really even have to go through and do all that linear regression stuff, but I'll show you that trick in a minute. If I go back to my sheet right here, right, you recall that I had R squared of 0.727273, right, and we said that that was the explanation. The sum squares of error, essentially we're looking for how much of the variation in our line is explained by our predicted line. Right? Well, if we take the square root of that equals square root of our correlation coefficient, that is what we call our correlation coefficient. So this is our correlation coefficient. What does that mean? Well, the correlation coefficient tells us something a little bit about the line. What it tells us is that if we had all of our points exactly along our predicted line, like let's take a look at these first two diagrams right up here at the top. If we were to get two correlation coefficients and they had a perfect correlation, that is, every single point fell right along our predicted line. It was 100% explained by that line. We'd say that there was a perfect correlation, r equals 1. By the way, if we had a negative correlation slope, r would equal negative 1. And so that correlation. What we say is that, well, if we actually do have a strong correlation between two variables and then they actually would fall along very closely to a line, well, this correlation coefficient tells us that if we have a number that's pretty close to 1, then it's a pretty strong correlation between those two, right? So like in this diagram right here, B at the top, absolutely, right? We have a very strong positive linear correlation. We could also say if it were negative 0.9, right? That would be a very strong negative linear correlation. In other words, the line would really pretty accurately predict what was going on. Now, if the line couldn't accurately predict, if those lines were spread out everywhere, right, a smaller linear correlation number like r equals 0.4, that's a pretty weak correlation, which means that our line doesn't do a whole lot to predict what's going on, right? Because you see all those points very far scattered around the line, right? But if we go back to our linear correlation right here, right, our happy mood versus sleep, right, we see, well, 85.85, that's actually a pretty strong correlation. According to our data, admittedly a very small data correlation, it looks like our data correlation is really pretty close, which is pretty good, right? Now, if we have no correlation whatsoever, there's just no values whatsoever, then we have right here what's called no linear correlation at all, right? No line would go to explain this particular setup at all. That wouldn't happen. Okay. So these correlation, right, that's what our correlation coefficient tells us. So if we looked at our line, right, we said our line right here, our best fit line, went like this. It said y hat, our predicted line, was equal to negative 3 plus 1 times x. Well, we got an r equal to 0.85 or so, and we said, well, this would be a very strong positive correlation. And what it means to us is that, well, if we were in the business of trying to predict whether or not our correlation was actually going, or whether or not our line, our best fit line, was going to be a pretty good predictor of whether or not more sleep meant a happier mood, right? We could say, well, okay, yeah, it should be, it should be pretty effective right here. That's a pretty strong correlation. And if I were to go onto my chart and say, well, what should I get if I get my requisite 8 hours of sleep, right? The recommended 8 hours of sleep. What should my mood be? Well, according to this, if I were to look over, I should have a mood pretty close to a 5, right? A happy mood of 5 as compared to somebody who slept maybe, 6 hours and only had sort of a lower sleep, right? So that tells us something. That's actually very, very useful. All right. So the relationship between correlation and the coefficient of determination is that the coefficient determination equals the square of that linear correlation coefficient, right? And we just demonstrated that in our Excel spreadsheet, right? So what we're going to do is we're going to do an exercise here where we're going to bring up the data set M body from our Canvas spreadsheet, and we're going to open that up and we're going to see if we can get a correlation going between these two. And I'm going to show you how we get the regression equation, the correlation coefficient, and whether or not we could characterize that as weak or strong. So we'll do that here in Canvas in the next video.